Hello, my name is Thomas Conrod, and I'll be giving you my report of Lab 3, beam vibration. Here's the outline of the lab. Okay, the laboratory objectives was to determine the properties through static analysis, um, analyze and then compare theoretical predictions with experimental results for dynamic systems, analyze the beam properties when applying an impulse excitation, um, analyze how viscoelastic damping influences the beam's behavior, analyze the impact of frequency modes on beam vibrations. Okay, the experimental setup, first shown in figure one, we have a ruler clamped down using a wood block and a metal edge to ensure that it's flat and not ruining the data from a student on the lab bench. We also have a Wheatstone bridge that is assembled on the right using 120 ohm resistors connected to a gauge and the DAC. The DAC reads voltages from a gauge on the ruler. Okay, more experimental setup shown in figure two. A different ruler is placed perpendicular from the first ruler and is used to measure displacements. The ruler is placed flat on a surface, and that surface is used as a reference point when measuring. As you can see, the ruler has a slight bend, so the data might not be as accurate as if the ruler is perfectly straight. Okay, sensitivity is which allows accurate displacement data to be gathered. Um, how we got sensitivity is different amounts of coins were placed at the end of the ruler, and we calculated the applied force, tip position, and average voltage, and we put them all on a plot. A linear trend was used to calculate sensitivity. Stiffness is directly related to how a beam responds to forces. The material undergoes elastic deformation and maintains uniform stiffness, meaning the beam behaves linearly. Shown in figure 5 is our graph, and stiffness is estimated from the slope of the load versus displacement. Okay, the first setup, case one. The metal ruler is held approximately 20 millimeters up using a reference ruler and then is released after 1 second. Displacement is greater when released and then it fades out. Um, as you can see in the graph, the release was perfectly on time with the 1 second. The displacement was only 15 millimeters instead of 20, which might have affected the data later on. Equivalent mass was measured and stiffness was calculated in the pre-lab, converting the beam into a spring approximation to match a spring mass damper system. These equations were used to do so. Since damping ratio is less than 1, the system is underdamped. This equation was used to calculate the theoretical response, and it went on the same plot as the experimental. We can see the theoretical response is slightly larger than the experimental. This is due because it overestimates the experiment because it is designed for a spring, not a ruler. There's a large spike for the first mode and no other spikes. The spike is a fundamental natural frequency. This is for case one. Fundamental natural frequency is 13.99 hertz, whereas before it was 14.099 hertz. Here is case two. A coin is released from approximately 4 inches above the ruler and bounces off. The ruler has a big initial peak and then also fades out. It has a positive higher peak first because that was the direction of the ruler at the first drop. Here's case two spectrum. This time it has two natural frequencies because dropping a coin on the beam causes multiple vibration modes, leading to the beam oscillating at multiple natural frequencies, which are shown on the plot. As previously, fundamental frequencies are just slightly off. Okay, the next step was using two different tapes to see how it affects the deflection. As you can see, different damping ratios were calculated. The lowest damping ratio was no tape since nothing was applied to the ruler. Scotch tape was very thin, so it had not that much of a different damping ratio, and the thickest duct tape, the highest damping ratio. Okay, finally, here's the final data. It was found that the different amounts of force and types of tape can affect the damping ratio. The more tape a beam has, the harder it is to bend, making a higher damping ratio. Conclusions. Beams without extra support have higher natural frequencies. With added supports like tape, stiffness, and damping ratios increase. Beams like a ruler show an underdamped response, meaning they isolate before settling. Additional conditions, including displacement, impulse, and viscoelasticity damping, play a crucial role in determining the beam's dynamic response and leading to the beam's oscillation multiple natural frequencies. Here's my work started. Sorry about the cold I have. Thank you very much.